Hi, Calculus. We're on unit number 3, and we're hoping to have some connections between real-life applications and the derivation that we've been doing the last 2 units. We're going to start with velocity and acceleration, and I'm hoping that we can make a model, a graph, and make those connections between a function and its derivatives. It would be particularly helpful if you would graph with me and use some different colors and maybe make those connections a little more visually. So our problem reads that we have a position of an object moving on a line, and it's given by the function s of t equals 6t squared minus t cubed. I'm not altogether sure why position is often given by s of t. I've heard it stands for scalar because position is just a single dimension. Sorry, I've got the flu. A single dimension. One class suggested s stood for stupid. But anyways, we're going to graph this function s of t equals 6t squared minus t cubed. I've used a bit of graphing software to help me set this up as well, but I have my time. I am going to use values from 0 to 6. I have my, let's see what fits here. T4, 36. Okay. I have a smooth curve. And okay, not super smooth, but we have an approximate s of t. So let's talk for a minute about what we see in this particular function. It starts at 0 and it's moving in a positive direction for this first piece. And then it gets a stopping place just for a moment and a turn in direction, and it's going to move in the negative direction thereon. Negative direction. So that's what we see in the function itself. We can see by various curves that there's a change in velocity here and there, and our velocity equation should help us with that. So we've been asked to create a model to represent the velocity, and the velocity should be that rate of change of the function with respect to time. So we are talking about a derivative. Our model can be represented by the change of a position with respect to time or velocity. The first derivative would be 12t subtract 3t squared. This is a quadratic that has t-intercepts of 0 and 4, with a vertex in the middle, if I'm going to sketch this, of 212. So I'm going to sketch this one in green. So this is our velocity, and it is a quadratic, 0, 4, and in the middle we have a value of 212. Let's have a look at that for a second. If our velocity is 0 at the very beginning, we should see our original function has a momentary rest. We also have a velocity of 0 at 4 seconds. And we should see a momentary rest in our original function, and we do. We can see that our velocity is positive for the first, well, for all of it. But we can see our velocity is getting greater, so we are speeding up. And After this turnabout, we are slowing down because our velocity is getting less. We should see that reflected in the blue graph as well. We are speeding up as we follow this curve, getting steeper, and then we are slowing down as we decrease that slope of that curve. Our maximum velocity appears to be at the 2-second mark. And it does appear to be the steepest point on that blue curve. I referred to the fact that the velocity is 12, but we could use a simple substitution to determine the velocity at 2 seconds. 3t4 minus t. We have 6 times 2. It is 12. So the velocity is 12 at 2 seconds. We're asked to determine and draw a model for acceleration. Acceleration would be the rate of change of the velocity with respect to time. We can write that as v prime t or s double prime t. It's the second derivative of the position function, or we can write that as acceleration. So our second derivative acceleration would be, I've had to go back and forth a bit, I've kind of forgotten, here's our velocity equation here, 12t minus 3t squared. So my acceleration, which is the derivative of velocity, is 12 subtract 6t. Let's sketch that on our graph as well. So the acceleration function is 12 subtract 6t, which is a linear function. We can see that the acceleration is greatest at time 0. Acceleration is positive for the first 2 seconds as we speed up, and then the acceleration becomes negative past the 2-second mark where we're slowing down. So our acceleration function does reflect our velocity, and our velocity reflects our position function, and it's good to see them visually to make some of those connections.